I'll take you to another very famous event. Here, you have Vesuvius. You see Napoli, the Bay of Napoli. Vesuvius right here, you see the volcanic cone from Google Earth. Of course, the famous eruption of 79 AD. If you look at our counting here again, 76, 78, 79, it's spot on. So we can say, some have claimed, you know, that our calendar is wrong, and during the Dark Ages, after the collapse of the Roman Empire, somebody forgot to count the years. But we feel that the Romans were right. It was 79 AD, and we arrive at the same. So it's a good check. We are counting the right way. Now, let's go to a very controversial little thing. Let's go to this place. I'm not talking about the Greek bankruptcy or anything. I'm talking about something entirely else. Here you have the tiny island of Thera in the Aegean Sea. Also a very volcanic area, but a whole lot more explosive and more erratic. And you can see the Middle East. This island blew apart sometime in the past. It's called the famous Thera or Santorini Eruption. Archaeologists have found lots of pottery from the Minoan culture buried also on Crete. Some of you might know Knossos and everything here, and what do you call it, Minotaur and things down here, but all this was buried, and the eruption was so big it really hurt the Minoan culture. Now, by looking at the pottery and the styles of pottery, they know they had a vast trade with Egypt. So they had a lot of Egyptian pottery that you find also here in the layers just below the ashes. So they know it was there when the ashes fell. By studying this pottery, they can say, this pottery is from the dynasty of Pharaoh so-and-so, because they have all the pharaohs of Egypt lined up in full battle array in a nice sequence. So they have it all right. If you use the standard dating method of archaeology, carbon-14, the first dates indicated something around 1500 BC. So 3,500 years ago. That sort of fitted well with the Egyptian dynasties, so everything was fine. By the way, it's most likely also exactly the same eruption that led to the biblical tale of the 7 plagues of Egypt. Because really many of those 7 plagues can be related to the volcanic eruption. The eternal night, ashfall, the frogs all over the place, the consequences of a tsunami up through the Nile Delta. All the frogs were simply washed out of the Nile, thrown up in the houses. The mortality rate went up because of fluoride poisoning. Later on it became the firstborn of each family. I don't think it was that selective at that time. And when Moses led the Israelis across into Palestine, he actually did not cross the Red Sea, but he crossed the Reed Sea, which is the Nile Delta. It was full of reeds. So he marched heavily across with the Jewish people, but when Pharaoh came after him, he was hit by the tsunami created by this volcano. And then the Jews went around over here following a fire column by day and a smoke column by day and a fire column by night. Yeah, of course, because they could see the thing. So it all sort of makes a little sense that there is a core truth in these tales. So that's why it's doubly interesting to see if we can fix this, date it. And lo and behold, if we go to Thera, this eruption, and we look at the acid curve from it, and we look at our counting, we actually find the acid fallout that we really believe is Thera. Our problem is it doesn't have the Thera name tag on it. But it happened 6042 to 6041 BC. This is 100 years and more. It's 140 years off the original dates. And it created uproar in the world of classical archaeology. Because now the classical archaeologists had to move the age of certain pharaohs And you don't move a king 150 years like that, because then you're missing a few below and you have too many on top. So, I mean, you can see, you have to rewrite the phone book. It was a really big thing. So, of course, this was cast in doubt for 20 years. We were sitting pretty alone at the side and said, yeah, I know we are climate researchers, but we have this and we cannot avoid it. Luckily for us, the latest carbon-14 dates at Thera are now at 1621 BC. So now we're only 20 years apart. And that's why I say, okay, we don't care to discuss anymore because that's basically the same. Considering the counting error we may do and the dating uncertainty, we're fine. Just accept it. So this is, I think, where we also have been able to move around in archaeology. I think this is deeply fascinating because once you get into a different subject and you start to work with carbon-14 archaeologists and so on, life as a physicist becomes a whole lot more fun. And you know what? I discovered one thing. Archaeology is definitely not an exact science. They can easily disagree whether 2 and 2 make 4. Easily. 2 and 2 is 5 in Cambridge, and 2 and 2 is 3 in Oxford. I can tell you that. So, another thing I would like to show you here is what also can be revealed by ice cores, because the ice cores are made of stuff from the cleanest environment in the Earth. Any tiny pollution that spreads all over the northern hemisphere will end up in Greenland as a signal. In the southern hemisphere, Antarctica will collect this for us. And here you have the fallout, or actually basically it's a ratio between copper and aluminium over 8,000 years. And what you see here is one of the earliest traces, about 2,500 years ago, of man-made atmospheric pollution through the mining of copper for bronze. What you see here is industry. It's people digging for metal, melting the metal, getting metal vapors into the atmosphere. That goes to Greenland and falls down. So we can easily follow that. We can also follow the Roman economy going up and down because we can see the pollution of lead by the Roman digging for silver in Spain. So every time Caesar ran out of money, he made some more silver coins in Spain, and the byproduct of that was lead. Some of that went up in Greenland. And of course, today, Greenland is chock full of the lead that we used to put in our petrol in cars. The upside of that is we can also measure today that the lead levels are going down because we removed the lead from the ice as well, from the petrol as well. So let's go further back in time. The Greenland ice core from North Grip actually turned out to be a stack of calendar years where we've been able to count 60,000 years back in time. It took us 20 man-years to complete the counting, so it's not something you do overnight. So this you have here is a climate curve, vertical on a time scale. But remember now that all these years are counted, so we know each and every individual year. The blue curves illustrate the isotope values. Warm to that side, cold to the other side. Up here is our present climate. The last 11,000 years. This is where agriculture developed. This is the Ice Age, the last Ice Age. And we never go into the previous interglacial because it's down here right now. But you can see we have a calendar, and what we have is actually, we have a curve that reveals that back in time, the climate has flipped a lot of times. And when you look at it for a while, you find out, hey, our 11,000 years are unique, not only because they're warm, but also because there's no zigzag to the curve. We have been so dead lucky not to have big climatic variations. And that's why I think that the reason why human civilization developed agriculture, cities, and things like that simultaneously in China, in the Middle East, in South America and things, they did that because the conditions were right. Even during the Ice Age, there was intellectual capacity to do it. But any agricultural tradition that would have started here would have been squashed by the repeated climate changes. Every 2,000 years or so, boom. Each jump here represents a change in average temperature in Greenland of about 14 degrees. Translate that into Europe, roughly 8 to 10 degrees on average. That's a lot. So how fast did they go? Well, if you expand that little thing up there, which is the very termination of the Ice Age, it becomes a curve like this, and then it doesn't appear so steep anymore. This is the change between Ice Age and present day. You see much more details. You see also a climate change here. So that's the little piece expanded. But we can expand that even further. We can study these. This is a warming, coming from cold getting warmer. This is a cooling, coming to cold. This is a warming again, and now the Ice Age is over. Actually, these periods have geological names. This cold period here, between the warm here and the warm here, this cold period is called Younger Dryas. This is called the Berling, and this is called the Ellerud. Also in French. And it's fun to hear French speaking these two words here. That's rather funny. And then you have all this Dryas down here. Because this climatic flip-flop, cold becoming warm, then becoming very cold again, and becoming warm, this zigzag, was first discovered and described in 1901 in Allerød Teglgrav, the clay pit at Allerød where they made bricks. They discovered in the clay pit a lake sediment, as the first slide I showed you, with mud. Gray mud and dark mud. Gray mud and dark mud. So they saw, hey, there's something going on in past climate there. And some guy started to look at the pollen, and he discovered that during this, what we call the Dryas period, which is cold, this one and down here, in Denmark, they found the pollen from the Dryas plant. That's a Latin name for the plant. In Danish is called rybeløb. It is a high Arctic plant you only find on the highest mountains in Norway today and in Greenland. It tells you this is tundra, no trees, high Arctic tundra. So at this time, Denmark was high Arctic tundra. Here, Denmark was high Arctic tundra, but here we're about 1,500 years, 1,500 years, where trees moved into Denmark. The ice had left, trees moved into Denmark. Denmark became beautiful, lush and forested. Then the climate deteriorated, the trees were wiped out, and Denmark became grass covered, and then the ice age kicked back in, and it became tundra for 1,000 years before the ice age finally ended. You can imagine what stress the ecosystem has been under with all these climatic swings. And they went very fast indeed. We studied the last one in detail. This is the most detailed record we have of the ice cores covering the end of the Ice Age. This is 11,850 years ago, 11,700 years ago. So this is 150 years, this is 150 years, this is 300 years in total. Each little pin here, each little dot here is 1 year. Over here you see a curve on isotopic ratios going this way and then jumping in level and all of a sudden becoming that level. This jump is completed in 1 year. This parameter tells us that all of a sudden, from 1 year to the next, 11,713 years ago, 14 years ago, the wind in Greenland started to blow from a different direction. The meteorological system simply reorganized itself. Then, as a consequence of that, average temperatures increased by 14 degrees in 25 years. This is completed in 25 years. The amount of dust blown in from China to Greenland decreased. This curve has inverse axis. It decreased by a factor of almost 100 over 25 years. And the annual snowfall increased by a factor of 2 in 5 years. All these parameters together indicate a massive climate change, triggered by 1 year to the next change of atmospheric circulation. So we have in Greenland evidence of climate flips that happens from 1 year to the next. Now, if you remember all the discussions from the newspapers these days about future climate with an enhanced greenhouse effect because we're burning fossil fuel, you will see all the models that are shown are soft growing curves. More and more CO2, more and more growing temperatures. And then they predict this, that, and the other. But none of these models can handle an atmosphere that actually behaves in fits and spurts. So, should you be scared? Yeah, slightly. Because what we are dealing with here is a system that is unstable. It only takes a little push to make it flip. And the trouble is, we don't know the triggering points. And maybe we already are operating one of them. So to give you an indication, how is it possible to warm up Greenland by 14 degrees in 25 years? I mean, entire Greenland. And not only that, this ice core record, the 60,000 counted years. How can I talk about global climate based on a curve like this made from Greenland? I mean, come on, give me a break. It's only a rod of ice, 10 centimeters diameter, and basically what it tells me is how climate was at that exact spot and nothing else. What about 100 kilometers away? Ah, it's ice, it's probably the same. Well, we have ice cores covering some southern Greenland cores, some central Greenland cores, and some northern Greenland cores. And you line them up and they tell the same story. So we are sure that the whole island of Greenland is involved in these climatic changes. What about Europe? What about the rest? Well, this curve is mimicked by stalagmites in China. This curve is mimicked by corals in the Bahamas. So the Greenland ice core record is the most highly resolved reference to any geophysical, geological evidence we have on climate change all over the northern hemisphere. So it is the carbon copy of climate variations in the north. So what about the south? Can we compare the two? Yeah, we can. We can go and compare them. Here we have the northern one. This is the green one. Now I'm lying it down again. You see, this is actually the present day climate. This is the longest record we have in Greenland so far. All this wibbity-wobbity is last ice age. And boom, goes way up there. This is the previous interglacial. And look at it. It's much higher than today. In fact, this is from a time 125,000 years ago when we know Greenland was 5 degrees warmer than today. And global sea levels were 5 meters higher, i.e. less ice in Greenland and Antarctica. This may be the climate we're heading for in the future. So this is nature's last natural parallel to a future we might be heading for. If we compare, the blue curve is now Greenland, the red curve is a similar curve at the same time scale from Antarctica. They're both covering one ice age. Present day climate in Antarctica, present day climate in Greenland, but you can see the curves agree on one thing. They agree on when the ice age ends, so that's a global phenomenon. They agree on when the previous interglacial stops, global phenomenon. So ice ages as such are global. Both hemispheres participate. But look now at the zigzag stuff in the middle. All these abrupt changes from one year to the next. This is pretty much more jumpy than the red one. That's one first logical explanation. The northern hemisphere is mainly land. And land has the ability to become very cold in wintertime and very hot in summertime. While the southern hemisphere is mainly water. So any variation will be much softer. But let's look in detail on them if we can combine the wiggles. So our colleagues did this. This is a Greenland ice core, again with the wiggly things, 50,000 years of it, all counted. Then, of course, in Antarctica, the trouble is you cannot really count the years because the layers are too thin. So you have to use other dating methods. So we were stuck with one little problem. We didn't really know the age. So we put them on top with the age we knew, or tried to know, calculate it. It looked like this. And then we said, give me a break. Look at the red curve. If you push it slightly to the left, everything will match. See that? It looks like it's offset to the right. You want to push it. Well, this top becomes that top and can go all the way. This looks off somehow. And we were tempted to do that. But luckily, the bubbles helped it out. Because if you start to measure the greenhouse gas methane in the bubbles in Greenland, you get a methane greenhouse gas concentration looking like this. I don't have all the details, but focus on these three because we have a lot of samples from this section. You can see what we call Big Brother and Three Sisters. Up here in the blue curve, they match exactly this Big Brother and those three sisters. So when it's warm, a lot of methane, and it's cold, less methane. But see, methane is a gas in the atmosphere. So if the methane content is high in the north, it has to be the same in the south because the air is mixed. So let's take the methane from the south and put on top. Oh, it's okay, they match. But they only match if the curves are offset like that. So what we've done here is we're using the variations in methane to synchronize the cores. So we don't have to know the exact age of the red curve because we know where it has to be put on top of the blue one. So they have to be offset like this. And now we start to understand what the heck is going on with these very fast climatic changes. Because we have a problem for physicists. Going back to how these happen. I told you that in Greenland, the temperature grew 14 degrees in 25 years. In Europe, they grew 10 degrees in 25 years. Stayed warm. All over North America, the North Atlantic, temperatures grew about 10 degrees in 25 years. That's a hell of a lot of heat. Who is paying that bill? Because the sun didn't shine so much more. These curves tell you what's happened. We stole the heat. We stole it from the southern hemisphere. It's a redistribution of heat that's already there. Every time it's cold in Greenland, the southern hemisphere warms up. And as soon as the heat kicks in Greenland, the southern hemisphere cools down. It's like a seesaw. In fact, it is what we have called the bipolar seesaw. It's the seesaw of energy going from north to south, from south to north. All controlled by the big ocean currents and the coupling to the atmosphere. So, in order to trigger these very, very massive climate events in the northern hemisphere, you only need one little goblin with a hand on the Danfoss thermostat at the equator. And he can turn the warm equator water north or south. I said the south, north is cold. I said it north, the south is cold. And that's what happened. And that's why we can explain how a tiny little change can really make big consequences. Does this bipolar seesaw exist today? And for that purpose, we go back in detail to see in our present very stable climate. I showed you there were hardly any variations. But if we go with a magnifying glass and look at the last 10,000 years, or 8,000, 7,000 years in this place, This is 5,000 years BC. This is 1 AD. This is now. So this is 7,000 years. This actually spans the entire history of human civilization. The blue curve behind me is the temperatures, and they are real temperatures. You can see them here in the black numbers, minus 32, minus 31, minus 30. This is Stone Age, coming into the Egyptian Empire, 5,000 first pyramids. Then during the Bronze Age, the northern hemisphere cools down. You have a minimum right here at the Roman ages. I think part of all the wars that the Romans had to fight along the borders and all the people moving around was because it was so cold in the northern wastes and in the steppes to the east that there was a pressure to come to southern Europe. Then it warmed up. This is 950. Interesting spot, because that's when the Vikings decided to settle in Iceland and Greenland. And then came the Little Ice Age. Boom. A drop from the Viking ages to 1600 of 1.5 degrees on average. A warming up in the 18th century, and a dip again, and this is the lowest point on record, 1850. Probably some of you have seen old photographs of glaciers. Now remember, photography was invented 1850. So if they took pictures of glaciers, they took them at their biggest since the last ice age. So when we want to stop emission of carbon dioxide and things like that, it's fine we stop emitting carbon dioxide to halt climate change. But don't wish yourself back to 150 years ago. At least not in these latitudes, because it was dreadfully cold and awful. I think it's okay as it is now. Actually, if I extend this curve, the most recent point is that we are actually about here now. So almost matching how it was during the Viking ages. And tell you what, they started to grow potatoes in Greenland again. Now, this variation is interesting. How did it look in the southern hemisphere? Like that. That's from an Antarctic core. And you can see, even in our quiet time, you can see the seesaw. When it's cooling in the north, it's warming in the south. When it warms up in the north, it's cooling in the south, and vice versa. So, there's a weak bipolar seesaw still there. And the trouble is, do we now kick so much to our atmospheric system with our emissions of carbon dioxide and methane that we are kicking this system out of kilter? So it starts to go self-oscillating again. That's the trouble. We don't know. Now, I want to finish with one little slide. This little thing. Last year we hit bedrock at Nîmes, and this is, you see, basal debris coming up with the ice. And if we do some analysis on this, I'll show you to you. Oh, there's too many pictures here.